Am I audible?
Yes.
Okay. So good morning, everybody. Let us get started. Let me share the presentation. Is the presentation visible?
Yes, sir, it is visible.
So we have been discussing about software testing and maintenance techniques. So I will do a quick. I mean, we have done a lot of introduced a lot of fundamental concepts which are straightforward. So I'll start with a quick recap from the verification validation process and then take through the new stuff. So verification, so I included this diagram. This is what you saw in terms of the VV model of software development, where this is where the development starts in the requirement phase. So starting from the wish list of the stakeholder, you come to specification, then get into detailing of that into analysis, design, then module interfaces, finally the classes. And then goes up the development implementation stream, where you have classes, modules, subsystems, one after the other getting built up and integrated. And finally, you have the deployed system. At every level, we have seen that a hierarchy of tests, starting from the unit test, then module level test, integration test, systems test, and validation in use, or what is known as acceptance test, will get done. So validation is this top layer where you are testing the final system against the specification. So you are checking if the system has been correctly built, whereas verification is this whole process of testing at every phase, whether the output of that phase conforms to its previous phase. So assuming that the subsystem specification is done correctly, your module interface specifications should have been done correctly. So when you come to the module and use the modules in the subsystem, the modules have been tested here. And then you go to the subsystem where you test if the modules are getting rightly integrated. So this is the validation process. So assuming that the modules are correctly done, you try to see whether the subsystem is behaving correctly. Right. So this is about building the system correctly. And it is both of them fall under the same framework, but naturally verification is a more detailed part, which we will keep on discussing at length. So we talked about that the design of test cases is the main issue, because exhaustive testing is not an option, and we showed that it may be possible given a simple program. The error could be actually detected by a small test suite. And from that, we came to three different main approaches to design test cases. I have added these diagrams. So one is the black box testing, which is also known as zero knowledge testing. That is where you are taking the entire application as a black box. So you put the test case input, and you have the test case output. You check whether the output is as desired. So obviously, acceptance test or the validation in use test will be this kind of a black box test. But black box testing will be done at every verification phase as well. White box testing, or at times called glass box testing, is looking into the system in detail, right? So here you see it is not a black box anymore. You can look inside each and every subsystem, each and every module, each and every class, and so on. And you can test every detail of this internals of the system. So you have a test case input and you have test case output, but that can happen for certain specific purposes of testing different details about how the system has been implemented. So white box testing keeps on building up as you implement the system into more and more higher levels. So it assumes that you have full knowledge about the system. So you know every detail of what is going on. And then you have a balancing, a mix in terms of gray box testing, which can be showed to be some knowledge testing. So it is neither black box that you do not know anything about the internals. It is nor white box where you know every details, but you may know details at a certain level of abstraction. And that's why it is called the gray box testing. So these are the main approaches. So obviously, gray box is a combined application of black box and white box testing. So what we'll focus primarily on are black box testing and white box testing in our discussion. Of that, the black box testing and white box testing, then let us just try to see why do we need both of them, right? You need black box testing because it's impossible to write a test case for every possible set of inputs and outputs, right? So you need to have representative test cases which finally test the system. You need black box testing because that is what your user will test, that is acceptance test. But black box testing in this process will try to always check that whether you are meeting the specification. In contrast, white box testing does not address the question of whether or not the program matches the specification. It is just looking for correctness. So, well, the correctness is directed towards meeting the specification, but whether it is actually meeting that or not is not in the scope of white box testing. So that is where they differ. In black box testing, you are looking at the whole thing as a black box. So there may be certain code parts which may not be reachable. I mean, you have written some code which is not getting executed or will never get executed. I mean, this is something which happens very often for the exception paths. I mean, they do not. I mean, you have considered an exception situation, but that situation actually never arises. So that is not reachable. On the other hand, in white box testing, it will not tell you if all functionality has been implemented because you are testing on the details of the system. So you test only what is implemented, right? You cannot test what is not implemented, right? So on the white box, on the black box side, there are implementations that you cannot test. On the white box side, there are functionalities that has not been implemented and does not get tested. So you need to do both of them. The third is it is often seen that you have written certain code, certain functionality which was not asked for in the specification, or which is not required for meeting the specification. So black box testing will not tell you that. Black box testing is happy as long as you meet the specification. So it does not tell if extra functionality has been implemented. Similarly, white box testing does not cover if there is certain program logic which is missing, right? So kind of they are complementary in nature. Just with one we cannot survive. We need both of them, and at times mix them in terms of the gray box testing. So I will not go through the details of the next couple of slides. The black box testing or functional testing or specification testing we have discussed. White box testing outline we have talked of. The structural testing. Gray box is a mix of that we talked of. And in black box testing, we have outlined that there are two main approaches: equivalence class partitioning and boundary value analysis. That you take the potentially infinite or at least very, very large input space and try to partition it into a set of equivalence classes so that all inputs in this equivalence class should behave in a similar manner. They have certain commonality of properties. Certainly with that, the partitioning has to be proper. At the same time, your objective always is to have as minimum number of equivalence classes as possible. Otherwise, a trivial equivalence partitioning could be that I have 2 to the power 128 possible inputs. So I can say that every input is a different thing. So it is an equivalence class, but that's not the idea. The idea is to find out some higher level abstract properties, which is common for a large number of inputs, and put that as an equivalence class and create representative test cases for it. The boundary value analysis on the other side tells you that when I have these equivalence classes, then naturally there is certain boundary of those classes. Right? So specifically, I can choose test cases which are inside the equivalence class, but I should make sure that I choose enough number of test cases which are on the boundary of these classes. So that often what happens that when you are inside the class, things go fine, but at the boundary things may fail. And I talked about a simple example of a for loop, which has an initialization part, a part to continue, and a part to actually exit from the loop. So part to continue is the common that you will test, but it is very important to test the initialization. What happens when this was not there and the loop is starting, and the exit condition. What happens when this loop closes up, right? So that is the kind of the boundary value analysis, and often you will find that there will be overlap of test cases which are already belonging to equivalence class may come as a boundary value analysis test case also, because it happens to be on the boundary. And naturally, the boundary value analysis test cases will may become overlapped with this, because they may fall in certain equivalence class. Often they fall in multiple equivalence classes also. Okay. So equivalence partitioning we have talked of, specifically this QES example we have seen, where a potentially very large input space of three coefficients, even if I take the coefficients to be of 64-bit integer, then I have 2 to the power 3 times 64, which turns out to be 192. So 2 to the power 192 possible inputs, but we are able to partition them in terms of 6 possible cases. And I'll show that analysis on the QES example more. And it is often possible to do this, and this is the characterizing condition. And then you choose at least one test case from every equivalence class. Often times what you do, you choose multiple just to make sure that, well, you are not testing for a very pathological case in the equivalence class. Often within an equivalence class, you might do a random choice of test cases also. Okay. So boundary value analysis in the same way we'll consider on the boundaries. And for the QES problem, we have seen that these are some of the boundary conditions where A is 0, where discriminant is 0. And this will particularly, knowing the implementation, this will become a very, very important boundary condition, because what you can do, you can generate some more equivalence classes for this. For example, if I go back, then what is the discriminant being 0? It is repeated roots, right? This one. I might want to actually, kind of partition this into 2 more subclasses for the purpose of boundary value testing, because we all know that when we do this discriminant analysis, then we may actually get a slightly non-zero value, a slightly positive or slightly negative value in the actual computation. That's particularly important when we have ABC that are not integer, that are, say, your floating point values. And finally, of course, we are going to take a square root of this. So that is obviously, whatever your type of coefficients are, that is going to produce a floating point value. So I might want to create 2 more classes out here, saying that, well, what is what exactly is a 0, and how do I ensure that is actually a 0? Do I do some checks for that specifically, or do I take that something which is very, very small, say less than say 10 to the power minus 8 or 10 to the power minus 12, in positive or in negative, is to be treated as a 0? If I do that kind of considerations, then those become, newly induced equivalence classes for my input. So I have to find out an equivalence class where this actually happens, right? And that is what is the outcome of the boundary value analysis, right? So it may be that you just get a a boundary value which is an equivalence class, or it may have some more. This is falling on the boundary of negative, 0 and positive. So between these three, so it is on the boundary of these three classes, right? Repeated roots, distinct and complex. So I might have to do some more analysis for that. So that's the whole philosophy of boundary value analysis, right? So this is up to which we had more or less done. So now we will go into white box testing strategies, right? So white box testing is testing the system, right? Not just the input output. So we'll test it in the system in multiple different ways. And two strategies for white box testing is particularly important. One is what is called coverage-based testing. That is, instead of course, we are checking if the input, given the correct input, whether I get correct output. But to produce that, what are the program elements that have actually used from the code? The program elements could be statements themselves, because that is the smallest unit that you can execute in most of the programming languages. It could be branches. Did I take all the branches that exist in the program? Did I check for all conditions in detail? Did I check for all possible paths that can happen in the program? And so on and so forth, right? So coverage-based testing, the more of the code that has been tested, gives you a better confidence, right? That this code is probably correct. I mean, you will never have 100% confidence, but it gives you a better confidence. The other could be fault-based testing, where I want to basically design test cases to expose certain category of faults. For example, I could say that everything input, output, everything is right, but does this function leak any memory? What is leaking a memory? Leaking a memory is allocating some memory dynamically. Then we have to hold its address. So I have done that, but before the variable that is holding the address goes out of scope, I have actually gone out of scope. But before the variable actually goes out of scope, I should have released that memory. I have not done it. So to the system, the memory is marked as being used by this program. But to me, I have gone out of the scope where the address variable holding that address was present. So I cannot access it anymore. So the memory has leaked. It is neither usable by others, nor I can use it. So this is also considered a kind of fault, because if you have done a lot of such memory leaks, then what will happen is you will consume a whole lot of memory, but you are not using them at all. So it is very possible that you will soon run out of memory. You may have observed many a times in your mobile phones. Of course, those are getting minimized these days. Is that it hangs, right? And then you just power it down and power it up, it works again. A number of times this is due to memory leaks. Because of memory leak, you have run out of the working memory in the system. And when you do power down, then the entire system forgets whatever memory was allocated, because all applications are closed, memory is reinitialized, and therefore it starts working again. In terms of the embedded system, this is a very, very important factor, because you are trying to build embedded systems which really usually does not shut down. So they have programs which really keep on running. They are not supposed to actually close, right? Other category of fault could be, are you doing, say, null pointer dereferencing? You have a pointer which is null and you are dereferencing that. So I want to specifically check for that fault. Now, obviously, if you have written the code correctly, then you would not have a null pointer dereferencing. Try to understand that issue, because you must have checked every time you are using a pointer. You must have checked that the pointer is not null, or you have checked the context where the pointer is known not to be null, right? But you may have missed out somewhere. So how do I check for that kind of a fault? Because I know that, I may have done a lot of coverage, but still these kind of faults might exist. So in fact, my test cases may not generate the particular condition under which a null pointer is getting referenced in the code. It could be a double deletion problem, that I'm trying to delete a memory that is already deleted, right? So there could be a variety of different faults that I might specifically want to check for, and white box testing strategies will have to cater for that. So we will see that most of the popular methodologies that I have talked of here, statement coverage to MCDC coverage, primarily takes care of the coverage-based white boxing. Whereas there is particularly mutation testing or certain types of data flow testing, which help you do the fault-based strategies. So that is a scope of what white box testing will talk about. Let me stop once here before I go into each one of these methodologies to see if you have any question at the generic level. Friends, if you have any questions, please feel free to ask. No questions. Okay, good. So let me continue. So going forward, what I'll do, I'll try to look into each one of the methodology, what it means, and what it is actually supposed to give you in the output. So this is the overall idea of the coverage-based testing versus fault-based testing that I have already discussed. Now, I would also introduce a few terms. What is the meaning of a stronger testing or a weaker testing? So kind of if you make a conceptual diagram of a Venn diagram of saying the set of elements that you are testing, then one test will be called weaker compared to the other if it is totally contained in the Venn diagram of the stronger test. So let's look at this one. So you have this lighter blue and you have this pink or magenta, whatever. So this is completely contained in this. So this lighter blue strategy tests these, and your weaker ones tests only this, right? So the weaker one is therefore called the weaker testing. Right? Then you could have testing which are complementary, like if you have a strategy 1 and a strategy 2. Neither is stronger than the other, because there are certain elements which get tested by both, but there are certain elements which only strategy 1 tests, or there are certain elements which only strategy 2 test. So we will have to see how does our testing methodologies position themselves in terms of strength and weakness and complementarity. Right? So starting with the first methodology, statement coverage, the concept is very simple. Design test cases so that every statement in the program is executed at least once. Right? So you have a program of 100 lines. So you're trying to make sure that every executable statement, of course, certainly commands and blank lines can be excluded, are executed at least once. Right? So the whole idea, the motivation behind this is, unless a statement is executed, we do not know if an error exists in that statement. Now, of course, if it is executed, still we do not know if an error exists, because we would possibly be executing it for only one input on which it may not have an error, but on some other it may have an error. But at least we are better positioned than if we have never ever given an input which executes that statement. So we do a coverage measure, which is a very simple measure, and it's very, very widely used in the industry, which is known as the statement coverage. That is the number of statements in the code that have been executed divided by the number of statements that your program has. So obviously this will be a number less than 1. So you typically multiply it by 100 and say my project has 73% statement coverage. So you can try to see the kind of statement coverage. How do you get? So here is a program function which is trying to find the greatest common divisor using Euclid's algorithm. So we assume the first statement to be covered, because anytime you call the function, this gets covered. Last one is also covered because it's just a syntactic one. So the remaining 1, 2, 3, 4, 5 statements are what we are looking at. Now, I'm saying that if I take a test case where I have equality, then I have checked this statement and have checked the return statement. Right? So if I take x is equal to 3, y is equal to 3, then these two statements are covered, the while and the return. If I take x greater than 4, y is equal to 3, then I check the while. I check this if conditions statement, and that becomes true. So I check x assigned x minus y. If I take y, x is 3 and y is 4, then I check the while, I check the condition, and I check the else. So I can say that this collection of statements, this collection of test cases gives 100% statement coverage. Now you may go deeper and argue that actually if I, for example, if I just give 4, 3, then that covers all the statements eventually, because if I give 4, 3, I will check for while, I'll check for the greater than, I'll check for x assigned x minus y, which makes it x becomes 4 minus 3, 1. So it becomes 1, 3. So after that, I will go back, check while again. With 1, 3, I will have a false case. So I will do the else, where y becomes 3 minus 1. So it becomes 1, 2. With that, I go back, do this, check the condition, do this again, it becomes 1, 1. And when it becomes 1, 1, I'm here, I'm checking the while, and I come to the return and I check that. So it is actually possible that one particular test case may check for more statements, but we are not getting into that deep analysis, or we may. But this at least clearly shows that if I take these 3, then it's very easy to analyze and say that these 3 will ensure that all statements are covered. Right? So this is kind of, and we don't, I mean, for getting 100% coverage here, we don't need to have a very large test suite. Along with this, if I have 5 more test cases also, my statement coverage is already 100%. Now, a second type, which I have not written here, but I will mention, is because it is very rampant in the industry use, is called function coverage. A function coverage is to make sure that if your project say has 1,000 lines and say 17 functions, have you called every function at least once, or there are functions which have not been covered at all. So again, it is measured in terms of number of functions that have been called at least once, divided by the total number of functions. And that percentage is called the function coverage. You can understand that if you have 100% statement coverage, you will have 100% function coverage, but not the reverse. So function coverage is usually easier to get. So often in the acceptance criterion of your white box testing, you will have metrics like that your code can be checked in, considered to be tested okay, if you have 100% function coverage and say 85% statement coverage, right? That's that kind of. Now, what you say is, what is the concept of a branch coverage? So if this will become very clear when we go to the CFG, but let me just give you the initial ideas at least. So branch coverage is checking for the branches. So branches are hidden here, unfortunately, right? It's hidden in the code. So here you have a while loop. So what you are doing, you are checking a condition. So the moment you check a condition, you have branches, and typically in languages like C, C++, Java, you will have two-way branching. I mean, some languages have multi-way branching. I mean, of course, no. I stand corrected. C also has multi-way branching in switch, but we can always visualize it in the model in terms of two-way branching. Right? So while has two branches, one when the condition is true, when you get in, and one when the condition is false, you go out to the return. Right? So there are two branches here, which is hidden. Similarly, x greater than y has two branches, one with assignment to x, one with assignment to y. So actually you have four, at two places you have two branches each. The question is, when I'm doing the condition check, did I check for all branches? So here I'm trying to make sure that how many of the branches I have actually executed. So it is the number of executed branches divided by total number of branches. Now it is easy to see that if you have covered a branch, if you have covered a branch, which means that you have taken both the true and the false parts of the branch. If you have covered a branch, then obviously all statements that come on the true path and statements that come on the false path have got covered, right? So branch coverage is therefore considered stronger than statement coverage, and it's more difficult to get 100% branch coverage in a code. Right? We'll see. Let me at this point, it is getting to be a very drab discussion. So let me at this point stop sharing this presentation and show you some tool results of, how does this coverage look like. I hope after doing this, I'll be able to switch. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay. So this is a coverage report from a project. This is a live project. This is a live report. Project is not live anymore. So this is something, as you can see, that this report was generated on 23rd March 2012. So exactly almost 9 years back. So this is a project that I used to lead in the company. This was for Toshiba in Japan, and EBM stands for electron beam machine. So we were building a mask writer for the ICs, electron beam mask writer. So it had to do with a lot of different geometry and so on. And 9K was a version number. So it was the 9000 version of that test. So for this converter, we created this coverage report. The report was created with a tool called LCOV. LCOV is a GNU tool, which is a free tool available. LCOV stands for line coverage, as you understand. So the entire project is run with this tool with a whole lot of test cases. Right? So, and the tool keeps on collecting what are the program elements that have been covered, right? And it produces a result like this, as you can see. So on left here, what you see is a list of directories. The project will have several directories. So it shows you the directory wise report. So it typically shows you report on the include and source directories. So here what it means is include directory is where you have the .h files of that module. So arbitrary mode flow for which you have the .h files here, and the source src is the directory where you have the corresponding implementation or .cpp files. So you can see all of them are those kind of directories. So this is the whole number of directories that you have. And then it gives you 3 different metrics in terms of line coverage, function coverage, and branch coverage. Right. So in terms of line coverage, it gives you these numbers mean that how many lines have been covered out of how many total number of lines. So if I look at this calculator SRC, then it is telling me that there are 397 lines in the source and 358 have been covered. So if you take percentage, it is 90.2% is a coverage. Similarly, here it is saying that out of 464, 373 lines only have been covered, right? And so on. Similarly, this is a function coverage report, which says that what is the total number of functions available. Say here, this is in calculator SRC. There are 88 functions, and 77 of them have been covered. So 11 of them have not been covered, which means that 11 of the functions have not been called at all on any input. Right? There are several which does not have a function. There are several where you have 100% function coverage. And finally, this is a branch coverage, which again in a similar manner tell you that what is the number of branches that you have in that code. So here there are 196. And of that, how many branches you have actually taken? So you have taken 80% of the branches, right? So you can see that it is possible that you have a line coverage which is 100%, but you have a branch coverage which is very bad. For example, you have an if condition without an else. Think about it. If you have an if condition without an else, you hit the if condition. And then on the if condition, there is some statements. You have done that. If it was true, let's say, and you have gone out. So what will happen that you have 100% line coverage because you have tested the condition, you have tested the true part, and you have gone out. But there is a hidden link, hidden branch, which is what if this condition was false? If this condition was false, then you are supposed to skip this and come to the end of the true part. Now this branch did not get tested. The statements got tested. Right? So the line coverage does not guarantee that you have branch coverage. But if you had tested both these branches, then obviously the lines would have been covered. That's the reason we say that the branch coverage is more difficult. Then you have in this report, which is very typical, certain colors, which is defined here. That is, what is the rating? That if it is less than 75%, this is low. If it is more than 90%, then it is high. And if it is in between, then it is medium. Now, these are settable parameters in your tool. So your manager will set these parameters for you. So this is what you'll have to meet. The target is to make everything high. Right? So that is how you color them. And you can get a very nice picture saying you that these are all green, fine. This is 77%, so less than 90%. So this is yellow. This is 65.5%, less than 75%. So this is red, and so on. And you can see that if you just look at this conglomerate of colors, you'll see that there's a function coverage is more green, because that's the weakest. Line coverage is less green compared to that, a little bit more of yellow and red, because it is stronger than function coverage. Branch coverage is almost entirely red here, because it is the strongest. So you have not been able to see many of those. Okay, so this is at a directory level. Let me just go in and show you some of the details. Let's start with a 100% case. 18, of course, very small, but let's look at this. So I've gone into this directory, fixed mode flow /include. So the level at which you are seeing the report was in terms of cumulative of the entire directory. But now you see it in terms of the specific files, and you see that you have 100% line coverage here, 100% function coverage. you have 100% branch coverage for this header file. Let us see what is that header file. Sliding window position.h. So now it takes you to the source. You can see that it has taken this branching here. So it says that branch is taken, 100% coverage for that. Let us see window position.h. It has 17 out of, sorry, where did it go? This is window position. So you see that there are branches which are not taken. Right? So it says that this is certain parts have been done, certain parts have not been done. Now, if I get back, let us look at some of the bad line coverage case. Let's look at a big case, medium one. Say output SRC folder. Output SRC folder. So it has 4 different source files. And you can see that in some the line coverage is bad, others it is moderate. Function coverage also is bad here. So let's see output buffer.cpp. Output. So this is the output buffer.cpp. So you can see a lot of lines marked which has not been covered. And see something interesting here. For example, let's say look at this. You can see this is a catch condition. Okay? So this is an exception handling path. And this exception handling path has not been taken. So as I was saying, that this is often the case that if you have bad coverage, you'll see how much of that is actually in terms of your exception flow. So this is a part of the exception flow. So this exception, which is a DPL : error kind of exception, has pointer type of exception which has not been hit. Right. So that's the kind of issues that you will analyze and find out, and then decide whether you really want to check for those and so on. We can end with something which is really bad. So let's say libvsb src. So this is another source folder, and it has so many files, and everything is bad at a cumulative level. Everything is bad here, and this is what you have. So you have something like out of chief configuration parser, only 198 of 332 are covered. So you can see a lot of, you can see error handler. So several of the error handling has not been done. All these branches have not been checked for. I mean, that is consequent, because if you have not done the error handler, this error handler, right? So you'll have several of that. So it is, I mean, your manager would say, okay, your happy path seems to be doing fine, but you need to really check for the error conditions, right? You are doing poorly in terms of the checking the exception conditions. So go back and check for those. Okay, so that's the kind of, and this is a cumulative result that you get, and possibly results in your staying back for the night at the office, because you'll not be able to check in with these numbers, right? Oh. So that was kind of an actual example of how these coverages, and this is, I mean, there are more advanced tools which gives you more stronger coverages, as we'll discuss, condition coverage and path coverage and stuff like that. But this is what is kind of very common in the industry to use, at least when you are doing a lot of systems level codes and so on. The coverages would be different from a GUI code and so on. So that is what we have. So let me get out of this and get back to sharing the presentation again. I don't think it is sharing. Is it sharing now?
Yes, sir.
Okay. So that was just kind of illustrative experience in terms of white box testing reports, in terms of statement coverage, function coverage, and branch coverage. Now, you see, if you have done all branch coverages, the question is, have you checked for all conditions? Suppose you have a compound condition. What will branch coverage require? The branch coverage would require that you set certain values, you get to set certain values for the digit high and digit low, so that the condition is true or the condition is false. If you have generated these two, then your branches are covered. But that does not necessarily mean that given the values of digit high and digit low, your condition is correctly computed. Because you have just, there are four possibilities, right? Digit high could be 1 or -1, digit low could be 1 or -1, four possibilities. Of that, you needed to use 2 to actually just test for the branch. But there are others which remain untested. You do not know whether this condition itself is correct. Right? If the condition is true, then what happens is correct. If the condition is false, then what happens is correct. But how do you know if the condition itself is correct? So condition coverage is the coverage approach where you check for every component of the condition, try to exercise truth values to them, true and false, and then check for the correctness. Right? So a condition coverage would measure the number of truth values taken by all basic conditions divided by 2 times the number of basic conditions. Right? 2 times because you have true and false. Right? Now, naturally, if you have done a condition coverage which is 100%, if you have checked all possibilities of all conditions, then obviously you have taken all branches. And if you have done that, it means that if you have a 100% condition coverage, you will necessarily have 100% branch coverage. So if you have checked for the conditions, then you have checked for branches, right? So condition coverage becomes stronger than branch coverage, which we have already seen is stronger than statement coverage. Right? So now, how difficult is this condition coverage or condition testing? Now, say a Boolean expression has n components. If it has n components, then the condition coverage require that you check for 2 to the power n test cases. Okay? Simple Boolean case. So that's exponential. So condition coverage based testing is practical only if this n is small. You have small number of component conditions. Otherwise, it will explode. So condition coverage, even though is very attractive, in its purest form, it is very difficult to use because of this explosive number of test cases that you'll need. So now then you question yourself, well, I have done a switching and automata theory course, right? You have done, right? Friends?
Yes, doing, sir.
You are doing, right? So you have done minimization of Boolean expressions. You have done Carnot map. You have done Quinn-McCluskey's method, prime implicants, and all that. So you know that for the final decision of a Boolean expression to be true or false, it is not necessary to evaluate all the min terms or the max terms, whatever you write, right? So we can try to make use of this information. A min term which is covered by other min terms may not be tested. Right? So what we necessarily do is, instead of generating all combinations for all condition components, we generate true false for some intelligently and leave the rest as don't care. That's precisely what your Carnot map does. That's precisely what your prime implicant Quine-McCluskey's method do, right? So that is the way, that is what is called modified condition or decision testing. In short, MCDC. So each condition must be shown to independently affect the outcome. So only those, the outcome of a decision, only when those which are independent will need to be tested. So an example. I have a Boolean condition here, A or B and C or D and E. And what I have given here, condition coverage requirement for the test cases. So obviously I have A, B, C, D, E, 5 Boolean variables, 5 condition components. So I have 32, 2 to the power 5, 32 cases of condition true, false, etc. This is below what I've given is the MCDC coverage test case. Here you see some I have shown as cross out. Cross out in terms of Carnot map means don't care. For us, it means that this test case does not need to specify the value of the crossed out condition variable. How does it work? Let's see. Let's take the test case number 6, which is F, don't care, F, don't care. So we are looking at the false of A, B, and D. So looking at the false of A, this whole entire table. Looking at the false of B is half of top, half of this table. Looking at the false of D. So it is these two, 0, 1. Test case 0 and test case 1. And test case 4 and test case 5. So we see that these 4 test cases 0, 1, 4, and 5 have A, B, and D as false. Right. Now 0 outcome is 0, 1 outcome is 1, 4 outcome, 0 outcome is false, 1 outcome is false, 4 outcome is false, 5 outcome is false. So we see that on all these 4, which have just A false, B false, and D false, the outcome is false. So I don't need to know what is C or what is D. It does not matter. It is inconsequential to that. Here E is changing, it does not change. Here in between here E, between these two, C is changing and it does not matter. So if I do this test case, then actually here I'm covering 4 test cases. So in this way, there is a, I mean, you know the minimization method. So I'm not getting into the details of how you do this coverage. You already know how to do that. This is 5 variable case, so you'll have to do the prime implicants Quine-McCluskey kind of. It's not easy to do Carnot map, but with that you know how to find out the main terms. And those main terms tell you what are the MCDC test cases. What turns out is if you have n number of condition, component variables in the condition, typically MCDC test cases tend to be within n+1. It's linear. It can be proven that it's linear. So from exponential, you reduce the problem down to a linear problem using this Boolean optimization idea. So MCDC is therefore very popular in terms of condition checking, that when you are doing condition coverage, you don't do brute force condition coverage, you do rather MCDC coverage. Okay, next is path coverage. We have just 2 minutes, so I do not want to get into path coverage. Let me, before that, show you something else in this time. This is for the quadratic equation solver. This is the solver code, which is a 33-line code here. And if you look at, these are the 33 lines marked. These are the equivalence classes which you need for the black box testing, and the representative test cases. And here, what I have shown is which equivalence class does it belong to, and then what are the statements that get covered by this up here, and what are the branches that get covered by this. You can try to solve this kind of a problem. Path coverage we have not discussed, so we'll come back to this in tomorrow's discussion. Let me know if there is any. Yes, please.
Yes, sir. As I asked in yesterday's lab, so like we are already implementing our lab project and test plan and test suite, and also the test cases of the lab project, and with the same time like doing the theory assignment. Like it's a bit too much considering like we have like 4 other courses this semester. So like
you have said this to teachers of each of the 4 other courses, right?
Yes, sir.
No, just kidding.
Like,
yes, continue.
So
what do you want?
Lab combined is more than all of the 4 subjects combined. If we look at the consumption of our time, that's why. So we just wanted to ask if you can take assignment 4 and 5 combined at a later date, like 5th or 4th, something like that. So
again, I would not like to have it combined. I would insist on a separate submission. But dates we can look at. You propose. I will talk to the TAs and then get back to you, because my constraint is there is a fixed date for grade submission.
Yes,
so
so
TAs
like,
have to complete that. So
exactly.
if you can talk to your friends, yes, and send me a mail. Send me a mail by today, saying what you propose to be the dates. Couple of days we can certainly look at.
Before evening.
Yeah. So because the idea is to learn. Idea is not to rush through for the grading.
Yes.
That's,
yes.
And the reason we have test plan, test cases, is exercise in both lab and theories. In lab, you have a freedom because it's a different experiment and different kind of languages and your choice of what you do. But
because
in theory, I'm trying to drive certain practices that you should be doing. So that is the reason we have it in both. They will be of different styles.
The reason because like I started doing it assignment 4 and the lab 1 at the same time, like 2 days ago, and at the current pace at which I'm trying, like I think like the assignments will be incomplete before the deadline for most of the people.
Yes, I'm saying that you suggest we will try to do our best in terms of considering TAs will also, I mean, they are also students. TAs will also have to be considered. So I'll try to because I have no hang-ups in terms of forcing you to do a bad job, right? Why should I try to do that? I'm trying to make you learn. So if you think that a couple of more days will help you in your learning, in doing a good assignment, I will try to do that. Let me know what you are proposing. Then I have to talk to the TAs and I'll decide that. Okay.
Okay. Thank you, sir.
Okay. Thank you very much. Then we'll meet tomorrow morning again. Have a nice day. And tomorrow morning at 8 o'clock, we'll continue on this. Bye.